Welcome back, dear students. Today we will learn about generalized Hooke's law. Generalized Hooke's law. Generalized Hooke's law. Before that, understanding generalized Hooke's law, we will understand what is Hooke's law. This is already taught. Hooke's law. Hooke's law says that stress is directly proportional to strain within elastic limit. Within elastic limit. Okay. Now see here, stress is directly proportional to strain within elastic limit, right? But for this, some demerits are there. The first demerit says, Hooke says that this stress is directly proportional to strain within elastic limit. This is one demerit. That is, above that one he did not define. Above the elastic limit he did not define at all. One thing. And the second thing is that this is applicable for uniaxial force system. Uniaxial force system. Uniaxial force system. Right? Then the second thing is that when a body is pulled in this direction, it will elongate its length in this direction. But Hooke ignored how much lateral contraction is happening. That when we stretch in this direction, obviously in a lateral direction there will be decrease in the dimension. But Hooke ignored that one. Means Hooke ignored Poisson's ratio. Poisson's ratio. See, these two drawbacks are there for the Hooke's law. Means we cannot apply this stress is directly proportional to strain when the body is subjected by force in 2 axes or even sometimes 3 axes. Why? Because he ignored the Poisson's ratio. And second thing is like this. Therefore, the Hooke only later words he invented and he suggested one law. He called it as generalized Hooke's law. Means what? This whatever it is said here below, that we can apply even for one dimensional, that is a uniaxial, biaxial, triaxial stress system. Okay, that what he says is, if a body is there in this way, 3-dimensional body, this is a 3-dimensional body. Let us consider this is a stress in x direction, then this is a stress in x direction in equilibrium. Next, this is a stress in y direction, this is stress in y direction, then stress in z direction and stress in z direction. If this is subjected with this one, then what is this axis? This axis is a z axis, this is a x axis, and this vertical is a y axis. Okay, now you are getting this. This is a 3-dimensional body. Then strain in x-axis. Strain in x-axis is defined as what? Then according to Hooke's law, strain is equal to stress divided by Young's modulus. This is for uniaxial when Poisson's ratio is ignored. But when you come to the strain in x direction, here strain in x direction equal to that sigma divided by E, sigma x divided by E, stress in x direction divided by E, minus, means this is a pure strain in x direction. When you don't apply a sigma y and sigma z, you will get a epsilon x equal to sigma x by sigma E. But I am applying in other direction also. See, the body when I am pulling this direction, it is coming this way, and this is coming inwards. But this force which is applied, which is taking it back, means when I apply here, then in the other direction it is controlling this stress, means this elongation. It would have come, when I apply only this force, it would have come this much long. But because of this force, this much long is reduced, it may come up to here only. Here this much of loss is there. Why? This loss is observed when we apply a lateral force. Therefore, thus that loss is how much? Poisson says that loss is mu times. Therefore, it is mu times sigma y by E. Minus, again in the z direction I am applying, therefore loss is there, mu times sigma z by E. Like that, if I write a equation for strain in y direction, then the pure strain in y direction minus mu times strain in x direction minus mu times strain in z direction. The same way, if I write a equation for strain in z direction, then sigma x sigma z by e minus mu times sigma x by e minus mu times sigma y by e. Okay, these three are very important strain equations. Strain equations when a body is subjected to three-dimensional stress system. Then it is very simple. If a body don't have any z force, then delete all the z terms. If a body don't have any y terms, then delete all the y terms. Like that, this equation will work out. This is called as generalized Hooke's law. Now, when we apply a three-dimensional stress here, this is a body here. When we apply these all type of stresses here, here and all, when we apply this one, then the change in volume takes place. The initial volume will be L, B, D, length, breadth, height, depth. Okay, this is a original volume. When we apply some stress to that one, the volume will change. That volume, change in volume, I will call it as a delta V. This is a change in volume. Then volumetric strain, I can define it as change in volume to the original volume. Change in volume to the original volume, I can write it. Now this, if I simplify it, what happens? See here. V is a LBD, and this change in volume, what I can write is, first I will consider delta L, change in length, and multiplied by BD, plus L into delta B into D. Then last term L, B, then delta D. This is called as change in volume. If I write this one into this equation, what happens, we'll see. Epsilon V equal to change in volume is this all, that is L delta L BD plus delta B LD plus delta D LB whole divided by V. Whole divided by V means what? This I will write delta V divided by LBD. Means whole divided by LBD means I can make it as a this divided by LBD and this divided by LBD, this divided by LBD. This meaning is whole divided by LBD only. Okay. Then now BD cancel, LD cancel, then here LB cancel. Then what is left here? Delta L by L is called as strain in L direction plus delta B by B strain in B direction plus delta D by D is a strain in D direction. Therefore, total strain, volumetric strain can be written as this way. This is very important equation. Okay, now think here, if a circular bar is there, then I will have a length as a one parameter, but in this direction is also a D and in vertical direction is also a D. Therefore, this volumetric strain will be equal to epsilon L plus 2 times epsilon D. This is for circular rod. If a spherical ball is there, spherical ball means this in all direction, in x direction it is a diameter, in y direction it is a diameter, in a z direction also it is a diameter. Therefore, total volumetric strain equal to 3 times strain in diameter wise. This is for spherical. This is all about volumetric relations or volumetric change. Okay. Thank you very much.